Hello, in today's video we're going to talk about the concept of mathematical induction. Let's consider the following problem and then we'll break it down from there. So let's start with the sum from I equals 0 up to n of I equals n times n plus 1. See if I can get my pen to work. N times n plus 1 divided by 2. And so let's just take some basic base cases. We'll toss in a 0 here. So we'll say if the left side of this equation is 0, then I'm taking the sum of 0 to 0, and I get 0. Does that equal 0 times 0 plus 1 divided by 2? Well, I get 0 plus 1 is 1, times 0 is 0 over 2, so yes, that checks out. Let's try for n equals 1. So if n equals 1, then I'm going to say 0 plus 1 equals 1, and then I plug in 1 for the right side of the equation, 1 plus 1, divide that by 2, and I end up with 1 times 2 divided by 2, and that equals 1, so that checks out. Now let's just do one more example number for some visualization. So we've got 0, we've got 1. Now for 2, we're summing up all the first three numbers, so 0 plus 1 plus 2. And we're going to plug in our 2 for n. So we're going to say, does that equal 2 times 2 plus 1 divided by 2? Well, 2 times 2 plus 1 is 3, divided by 2 equals 6 over 2 equals 3. And that checks out because 2 plus 1 is 3 and 3 are equivalent. What we've just done is the first step in mathematical induction, and we're going to call this first step the base case, or the basis step. The basis step is where we prove the base case, which happens to be 0, and we've done that. From there, our goal is to prove that it's true for any arbitrary integer that you pick. And so let's say I wanted to go down to infinity or some really, really high number. I don't want to have to do that by adding up each individual one, but I want to have security in that the formula is correct. So mathematical induction is going to allow me to do that. So mathematical induction has two steps. The first one we've completed, the basis step. And then the second step is what we call the inductive step. And we're going to do that next. So let's write this out. On the left side here, we'll say that the inductive step contains what we call the inductive hypothesis. So the inductive hypothesis is the first portion of this. And what I'm doing is I'm going to pick some arbitrary integer k. And now what is k? You'll find that most problems use the letter k to represent an arbitrary integer, meaning if I choose some arbitrary integer k and I plug it into my proposition, which p of k is the proposition that this formula works, then if that's true, then our goal will be to show that p of k plus 1 is true, which is the next one in the iteration. So we're not necessarily saying that p of k is true per se, but we're going to say let's assume that it is, and if it is, then that implies p of k plus 1 is true, and we're going to show that p of k plus 1 is true based off of that assumption. So back to the hypothesis piece. My hypothesis says let's assume that the statement is true for some arbitrary integer k. So if I'm going to do that, I've got to rewrite my statement. So I'm going to write 0. I'm actually going to expand this out to 0 plus 1 plus 2 up to dot 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 k. And I'm going to say that that's true for k times k plus 1 divided by 2. So let's just write the word assume here, because that's what I'm doing. This is an assumption. And based off of that assumption, I need to show something. So I need to show that 0 plus 1 plus 2 plus dot 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 up to k plus 1 is true. But if I'm going to do that, I have to replace or substitute in the plus 1 into my k. So I'm going to say k plus 1, and I'm going to multiply that by k plus 1. And let's not forget to keep our original 1, so k plus 1 plus 1. And then I'm going to divide that by 2. So to simplify this a little bit, it's going to look like this. It'll be k plus 1 times k plus 2 over 2. And then if I FOIL this out, it's k squared plus 2k plus k plus 2 all over 2. All right, and then of course I can combine the 2k and the k equals 3k, and that's what that looks like. So this is the right-hand side of our equation here. Let's get a lighter color. This is the right-hand side, and the question is, does that equal the left-hand side? This is our big question. And if the answer is yes, then I have proven that p of k plus 1 is true. So what do we know? Well, we know that we have an inductive hypothesis, which we are assuming to be true. And since we're doing that, we're going to be able to replace or substitute in this portion for our inductive hypothesis by just rewriting k times k plus 1 divided by 2. And then we're going to add that next iteration of k plus 1. And our right side isn't going to change. I can just rewrite it as k squared plus 3k plus 2 divided by 2. And can we make the two sides match? Let's start by getting a common denominator. And in most of these problems, you'll find that that's what you have to do. And so for this one, I can see that I need a 2 basically over 2, because that'll allow me to combine this into one fraction on the left. And I can rewrite it out. So let's just expand out, first of all, our k squared, because we're going to distribute, plus k. And then we're going to add, and let's distribute this, 2k plus 2, and all of that is over 2. And you can see that 2k plus k is 3k. And now let's take a look at the right and see what we have left. Well, we've got k squared equals the k squared. This 3k equals this 3k, and then this 2 equals this 2. And so we've got an equivalency. So what this says is that this mathematical inductive proof is complete, that they do match, and therefore I can conclude that this statement is true for all of n. Let's try another one. Let's try 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed. And let's say that equals n times n plus 1 over 2 quantity squared. So this whole thing is squared. And like the last one, we're going to start with a base case, and we're going to say, okay, let's plug in our first one. So let's say our base case is 1. And what is 1 cubed? Well, 1 cubed is just 1, so great, that's the left side. What is the right side? Well, the right side is 1 times 1 plus 1 divided by 2, quantity squared. And what does that equal? Well, 1 plus 1 is 2. 2 times 1 is 2 over 2 equals, and then we square it, and that equals 1. So yes, that's a check. We could do the same thing with 2 and with 3, but we're not going to for this. Just this is our base case. We only need 1. The next step after the basis step, because this was the basis step that we just did, is the inductive step. So we're going to write down inductive step. And we're going to say, okay, well, the first thing we need is our inductive hypothesis. So the inductive hypothesis is going to be that P of k is true for some arbitrary integer k. So I'm going to write out 1 cubed plus 2 cubed plus 3 cubed plus ... up to k cubed. We're going to say that equals k times k plus 1 divided by 2 quantity squared. Now, this, again, is what we are going to assume. So that's what we're going to use to substitute later. Now, next, we will show something. We're going to show that 1 cubed plus 2 cubed plus 3 cubed plus ... up to k cubed plus the next iteration, which is k plus 1 cubed. We're going to show that that equals, and just like last time, we're going to start with our k, and then we're going to add 1 to it, and then our next k, and then we're going to add 1 to that, plus 1, and we're going to divide that by 2, and then we're going to square the whole thing. Okay, so this is what we want to show here. We want to show that the left side of this equation is equal to the right side. And in order to do that, we have to manipulate the numbers so that we can prove it. The first thing we know is we know that we're, based off of our assumption, that the first k elements of this is going to be equivalent to k times k plus 1 divided by 2 quantity squared. And then after that, we need to add our next iteration, k plus 1. We're going to cube it, and we're going to say that that equals k plus 1 times k plus 2 divided by 2 quantity squared. All right, cool. Now let's simplify the right side just a little bit more, because I don't like all these extra squareds running around. And so k plus 1 squared is here, okay, and then k plus 2 is also squared, and then the denominator, we're going to square that, so we've got 4. Now on the left side, we have another one that has a squared over the whole thing, so I don't like that either. So let's just break that down. Well, k squared is here, so we've got 2 k's. So we'll just write it out like this, k and k, which is k squared. And this next to that is k plus 1, and we're squaring that as well. And we're dividing that whole thing by 2 squared, which is 4. And then we're going to add k plus 1 cubed. So just like the last problem, we need to get a common denominator. And in order to do that, we're going to multiply this here by 4 over 4. And that will give me the 4 that I want in the denominator. And, you know, just because we're at it, since the right side has a 4 over it already in the denominator, then let's just cancel it all out by multiplying both sides by 4. So that would go away, that would go away, and that would go away if I multiply both sides by 4. So now we don't have to write the denominator at all anymore. And the next step is to look at what we have left. Well, I've got let's see, I've got k plus 1 on the left-hand side. So let's just accent that we have a k plus 1 cubed here. And we've got a k plus 1 squared here. So I could pull both of these out to the front. And the reason why I say that is because I have a k plus 1 squared here that needs to be pulled out. So let's do that. Let's do k plus 1, and we're going to square that. And we're going to multiply the whole thing by k squared, because if I redistribute this, I will end up with k plus 1 squared times k squared, which I've already got in the green. And I'm going to add, well, I've pulled out 2 of my k plus 1s. And I'm left with 1 k plus 1, and I also have a 4. So let's write down 4 times k plus 1. So now I have a k plus 1 out front, a k plus 1 out front, times something on the left, and times something on the right. So my question is, does the left portion here, does this equal this? And we can find that out easily by just, let's expand k squared plus 4k plus 4. And then we're going to say that that's multiplied times k plus 1 squared. And then on the right-hand side, I'm going to take my k plus 1 squared. And then let's FOIL out k plus 1 squared. FOILing that out gives me k squared plus 2k plus 2k is 4k plus 2 times 2 is 4. So as you can see, this matches this matches this, therefore we have an equivalency, and our proof is done. So to summarize, we did our base case. We said our base case was 1, and we proved that that was true. We assumed that some arbitrary integer k was true for the hypothesis, and then we showed that that was true for k plus 1 by making sure that both sides of the equation were equivalent thereafter. So that is all for that. Let's do one more, and I feel like we should be good after that. Okay, so the next one is going to be a little bit more complicated, but again, it's the same steps. As long as you get the same steps in the right order, you'll be fine. So the next one says, let's take the sum of from j equals 0 to n of negative 1/2 to the j, and we're going to say that that equals 2 to the n plus 1 plus negative 1 to the n. and then we're going to divide that by 3 times 2 to the n. So we're going to start with our basis step. So our basis step says that we will plug in the first value, which in this case is 0, and by doing so on the left, we're saying negative 1 over 2 to the 0, which happens to equal 1. We're saying, does that equal 2 to the 0 plus 1 plus negative 1 to the 0 divided by 3 times 2 to the 0. And, well, 2 to the 0 plus 1 is 2 to the 1. 2 to the 1 is 2, plus negative 1 to the 0 is 1, divided by 3 times 2 to the 0 is 1. And is 3 over 3 equal to 1? Yes, it is. So that checks out. That's the basis step. And the next step after that is the inductive step. So we'll just write this out on every problem. We'll write down inductive step. And then the first portion of the inductive step is our hypothesis. So we'll take our hypothesis as the sum of, and I'm going to write it out, negative 1/2 to the 0 plus negative 1/2 to the 1 plus negative 1/2 to the 2 plus dot 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 up to negative 1/2 to the k. We're going to say that that's equal to 2 to the k plus 1 plus negative 1 to the k divided by 3 times 2 to the k. And so this is our assumption. So I'm going to write down assume. And because I'm assuming that, that's what I'm going to use to substitute later. So I'm going to say what I want to show is next. So I'm going to show that negative 1 over 2 to the 0 plus negative 1 over 2 to the 1 plus all the way up to negative 1 over 2 to the k. And then I need to add my next iteration, just like the last problem. I'm going to say plus negative 1 over 2 to the k plus 1. And we're going to say that that's equal to 2 to the k plus 1 plus 1, because there was already 1 there, plus negative 1 to the k plus 1. And then we're going to divide that by 3 times 2 to the k plus 1. And this is what we're going to show. And in order to show that, we have to show an equivalency between this side of the equation and this side of the equation. We know that our inductive hypothesis is what we are assuming to be true. So with that, we can substitute everything up to k with the hypothesis by rewriting 2 to the k plus 1 plus negative 1 to the k divided by 3 times 2 to the k. And then we are going to write the k plus 1 element, and we're going to set that equal to 2 to the k plus 2 now, plus negative 1 to the k plus 1, and that's all divided by 3 times 2 to the k plus 1. So the first thing we're going to do is the same as last. We need to get common denominators and then ultimately work our way towards an equivalency. So in order to do that, I need to think to myself, well, what do I want on the left side? Well, I want 3 times 2 to the k plus 1. And on the left, I need to just get them together first, and then we can go from there. So let's start by multiplying the first portion of this problem by 2 over 2, because that's what I have in the denominator over here. And in doing so, I end up with, in the numerator, 2 times 2 to the k plus 1 is 2 to the k plus 2, plus, and then I have negative 1 to the k times 2. So we'll just write 2 times negative 1 to the k. And then in the denominator, I'm left with 2 times 2 to the k is 2 to the k plus 1, and times 3. And then I'm going to add. In the numerator, I've got negative 1 to the k plus 1. And I'd like to multiply that by 3, actually, over 3. And so then that'll give me a 3 here. And then in the denominator, I'm also multiplying by 3, but I've got first the 2 raised to the k plus 1 times 3. Now you can see that our denominators match here and here, and also, coincidentally, it happens to match over here too. Just flip it around, but it's the same thing. So that's great. If our denominators match, well, what doesn't? So let's just go through and see what's left. We just identified that the denominators match. The 2 to the k plus 2 matches, and it's plus something. And so the only thing that doesn't match is this and this. So I need to figure out if that is equivalent. So I'm going to write this out. Let's just figure this out really quick. What I'm saying, or what I'm asking, I should say, is it true that 2 times negative 1 to the k plus 3 times negative 1 to the k plus 1, is it true that that equals negative 1 to the k plus 1? This is my question. So at first glance, it may not seem obvious, but let's just work this out. So let's say that 3 times negative 1 to the k plus 1 is the same as saying 2 times negative 1 to the k plus 1 plus 1 times negative 1 to the k plus 1, because 2 of something plus 1 of something is 3 of something, right? So that's an equivalence. So let's just, rewrite this now as 2 times negative 1. So I'm going to rewrite this portion here. I'm going to say 2 times negative 1 to the k, and then I'm going to rewrite this next portion here by saying plus 2 times negative 1 to the k plus 1 plus 1 times negative 1 to the k plus 1. And well, what do I know about looking at this? Well, I know that 2 times negative 1 to the k, well, did I say 2? Or that should be k. This should be k. Having trouble getting my pen to work. 2 times negative 1 to the k plus 2 times negative 1 to the k plus 1, this just equals 0. And if this equals 0, that leaves me with just this, which is what I was looking for. Because remember, my question was, does this equal this, but if this equals 0, then it just cancels out and goes away and leaves me with -1 to the k plus 1. So now that I know that those two are equivalent, and that was all that was left, that actually pretty much completes the proof. So we could finish this out by just writing the same thing twice and just saying that 2 to the k plus 2 plus -1 to the k plus 1 divided by 3 times 2 to the k plus 1, which is from the left side here. So this is what I'm saying. And I'm saying that that equals this. And because these two are equivalent, that completes the proof. So a lot of work that we wrote on this board, but hopefully you're able to follow along. And that is basically it. So in summary, any inductive mathematical induction that you're going to do, you're just going to take the equation, you're going to start with the basis step, which should be easy points. You just put it in with the base case, and if you prove that equivalency, from there, you move on to the inductive step, which begins with the hypothesis, and the hypothesis is what you're assuming to be true, and then you substitute that in to your equation, and then you add the k plus 1th element, and then from there, you just work out the math. So hopefully you enjoyed the video. Feel free to rewind if you need to go over some of it again. But that concludes our video for today. Thanks for watching. Bye.